Hello everyone. In the last class we had discussed about the Gibbs paradox. Today we will be discussing about how to solve the Gibbs paradox. So let us begin. So we had a situation where the entropy was having some issues regarding mixing of two ideal gas of same nature or two same ideal gases, and the entropy which was supposed to be the change in entropy which was supposed to be zero was not zero. So the solution to Gibbs paradox was suggested by Gibbs himself. He said the correction in the number of microstates. Generally, the number of microstates in this case, we have, in the explicit calculation we had taken as gamma. So here omega, sigma, they are all calculation of microstates. So this gamma should be reduced by a factor of n factorial. So this expression gamma was reduced by n factorial, and then when you use that, you will get an expression like this. We know the ln gamma was given by n v by h cube 4 pi me by 3n raised to 3 by 2 plus 3 by n. We take ln gamma, and this comes out to be divided by ln n factorial, which is equation number 1. Now here you can use this Stirling's approximation. Log n is equal to n log n minus. So here, using that approximation, you will rewrite the equation because it is in the denominator. Log comes out as minus n log n, and minus n becomes plus n. So here already you are having a 3 by 2. So this will become 5 by 2. Then ln gamma comes out to be. Bring this ln log n to this term. So this comes out to be v by h cube n. N is common, n log n, and then v by h cube n 4 pi me by 3n, 3 raised to 2, 3 raised to 3 by 2. Now, so the modified expression for entropy of an ideal gas, we know entropy is given by K ln gamma. So here we will write it because we are again going back to the partition where with having two gases. So we will write a general expression SI. So where SI is given by, you are rewriting the expression as Nik ln Vi Ni plus 3 by 2 Nk plus 5 by 3 plus ln 2 pi Mi Kt by h square. Here this, now here V by Ni is something which will affect the whole process, because in the beginning we had written only ln V. Now the look of it itself, from it we can realize that this is an extensive property. Earlier entropy we found out that it was not extensive because when you multiply by a factor alpha, then the entropy should come out to be alpha s, whereas it was not there in the previous case. Here you will see, there you are getting a factor of alpha v. Here we will not get that because this alpha v and alpha n will get cancelled. So finally you will get an alpha n. So entropy S prime will be equal to alpha n, which is correct. So this is extensive from the expression directly, and using in the Gibbs thought experiment, that is the difference in entropy. So difference in entropy will be S total minus Si. That is, you remove the partition, mix both the gases. In the case of ideal gas, both gases are same. In the cases of same gases, both gases are same. So there, here the difference in entropy is given by delta S is equal to St minus Si. Si is actually both. So we will write N1 plus K ln V1 by N1 plus 3 by 2, 5 by 3 and plus N2 so and so. So finally this term is not relevant. This will go. This term will also go. This term will make the difference. So the total of this term will be what? K N1 plus N2 total N, ln V1 plus V2 total V N1 by N2 minus N1 ln V1 by N1 minus N2 ln V2 by N2. This one more step is there which you can do very easily. Now this modified expression for entropy incorporating the Gibbs correction is known as the Sackur-Tetrode equation proposed by Sackur and Tetrode in their research paper. So this is the expression, the modified expression for entropy. Now here, to check whether it is correct or not, we have to check whether this delta S is going to 0 for mixing of two same gases. So let us see here. Now we take the, for same number density, N1 V1 is equal to N2 V2 is equal to N1 plus N2 by V1 2 plus V2, which is generally for a same gas. substitute this here. When you substitute this here, N1 by V1 is actually what? N1 by N2 plus V1, V1 by V2 plus by N1 by N2. So take N1, first term comes. Similarly here, take the second term. Both the terms cancel each other. Finally, equation 4 becomes delta x is equal to 0. So this expression is also suitable for a gas, same gases mixing together. Hence, we have resolved the Gibbs paradox. Once you have resolved the Gibbs paradox, let us try to derive our standard thermodynamic equations from it to validate that this expression is correct. So we know the new expression comes out to be, we have slightly inserted this whole expressions inside this brackets. So the new expression is nk ln v by nh cube 4 pi me by 3n raised to 3 by 2 plus 5 by 2 nk. So here bring s 5 by 2 nk to the left hand side. And so s minus 5 by 2 nk by nk divide by nk ln so and so. Then what we do, this is power. So insert whole thing inside the power. So that the ln raised to 3 by 2 comes out to be 3 by 2 ln. So v becomes v raised to 2 by 3, because for v to exist inside the power it should be 2 by 3, no? So that 2 by 3 into 3 by 2 is v. So it comes v raised to 2 by 3, n raised to 2 by 3, h into 3 into 3 by 2, h into 1 by 3 into 3 by 2 comes out to be h raised to minus 2, which is h square. 4 me, 4 pi me by 3n. It comes up because you are using a logarithm. So finally bring 3 by 2 to this side, and finally you will get an expression of energy as 3h square n 5 by 3 by 4 pi m v raised to 2 by 3 exponential of 2s by 3 nk minus 5 by 3. Now let us derive chemical potential from it. From our thermodynamic potential expression, the thermodynamic potential can be taken as dou E by dou N, Vs fixed. So here you when you do it, take this is a constant part, no? Take this as outside. So there N is coming in two expressions, so we can use the product rule. So differentiation, take fix this, vary this and fix. First differentiate with respect to n raised to 5 by 3. So you will get n raised to 5 by 3, n raised to 2 by 3. Keep this fixed. Then keep this n 5 by 3 fixed, vary this. And finally, then manipulate such a way that you are getting, already you are having 3h square by 4 pi m v3. Take the exponential common. So this comes out to be v, e. This comes out to be e. E into 5 by 3n minus 2s by 3n square k. Now, moving further, we will get mu is equal to E by 5 by 3n minus 2s by 3n square k. Now substitute for E. E is 3 by 2 nkt, which we have done before in the explicit calculation of microstates. Substitute here. So 5 by 2 nkt, here also 2s into 3 by 2 nkt. 2se, no? So 2 cancels. Here 5 by 2 nkt by n minus ts by n. What is 5 by 2 nkt? PV is equal to nkt, E plus PV is equal to 5 by 2 nkt. So 1 by n, E plus PV minus ts. And what is this? This is the Gibbs potential. Gibbs potential is E is equal to E plus PV minus ts. So this whole thing can be written as G. So mu is equal to G by n, G is equal to mu. This is again one of the standard definitions which we know already. So from this we are able to derive. So this expression is okay because you are able to derive the standard thermodynamic parameters from it. Now let us further do some analysis. Again let us write down E. Make log. Then you will get 2s by 3nk minus 5 by 3. And then what you do, you simplify, you reverse it, 5 by 3 minus 2s by n, because you are having an expression in that form, 5 by 3 minus 2s by nk. To reverse it, what you do, you this reverse, take a minus sign. So what will happen? Numerator will become denominator. So then multiply E on both sides. Multiply here, multiply E here. What you get is E ln 3h square 5 n 5 by 3 4 pi m v raised to 2 by 3 is equal to n mu. Let me tell you, this is mu. So that we had done all earlier also. This is n mu. Again E is equal to 3 by 2 kt. So mu is equal to 3 by 2, nn cancels, 3 by 2 kt ln 3h square v raised to 5 by 3 n raised to 5 by 3 by 4 pi m v raised to 5 by 3. Here we already know that chemical potential is an intensive property. So if you change n to alpha and v to alpha v, you will not get alpha mu, because you will get only mu. That is the property of an intensive parameter. See, because the alpha will get cancelled. So we already know it's an intensive property, and again from deriving it, we are also getting an expression where it shows it is having intensive property. Now moving further, let us we know this is the Helmholtz free energy, which is given by E minus Ts. E minus Ts can also be written as G minus PV, because G is actually E plus PV minus Ts. So E plus PV is minus Ts. So we will write G minus PV. This we already know, this expression. So we can, and PV is equal to NKT, that also we know. So we will get an expression where A is equal to NKT ln n by v h square by 2 pi mt kt raised to 3 by 2 minus 1. Now in this case, A is an extensive property, also has been proved from this expression. See, if you multiply a parameter alpha, in this case a logarithm, no issue, it will get cancelled, but there will remain an alpha here, such that the new A prime is equal to alpha A, which is the basic nature of any extensive property, that you multiply a parameter, the new one comes to be as alpha A. So here we have tried to prove that both mu and E are look to be extensive even directly from the definition itself. Now let us summarize what all we have done. First thing, this is the highlight of the whole presentation, is that we were treating ideal gas as distinguishable, giving an expression of entropy which does not show extensive property behavior. Further, in case of mixing of same gases, it leads to delta S greater than 0, which is the Gibbs paradox. This we had derived in our previous presentation. So here what we have realized, that ideal gas can be treated as an identical particles, but not distinguishable always. Therefore, it leads to Gibbs paradox. Gibbs paradox is solved by decrease the number of microstates by a factor n factorial. And what is the logic behind it? We have treated the particles to be indistinguishable. So here some quantum mechanics comes into picture. Something like when you do some permutation combination, there is a chance of repeated counting, and therefore we divide by a factor to get the correct number. That is the logic we have used here. So ideal gas, whenever we say classical ideal gas, we cannot completely solve it using the concept of distinguishable particles, because these particles have to be treated as indistinguishable to get the correct entropy and other parameters. So, and solve the Gibbs paradox. So we have done both, and then we found out the thermodynamic quantities mu, E and A obtained from the corrected expression of S, validating the correction made in the number of microstates. So this is the summary of the presentation. So that's it. Thank you.